Welcome back, everybody, for lesson 4, I think, of the chemistry unit. So today we are going to go through some more of the Bohr diagrams, just finish that up, and then work on the periodic table. So looking at my final Bohr diagrams that I've drawn here, you should have something similar after you finished your work that I left with in the last lesson. And one of the things we want to look at is sort of the trends that we see. So notice here that the hydrogen, lithium, and sodium all have 1 electron in their largest orbital. Beryllium has 2 electrons and 2 electrons, and 2 electrons for magnesium in the largest orbital. Fluorine is missing 1 electron, so is chlorine. Helium has a full shell, neon has a full shell, and argon has a full shell. So this is a really, really key observation that we want to make in studying Bohr diagrams, especially Bohr diagrams along the periodic table. So we notice the alkali metals, that's this group here. So oops, let me just change my pen down. So alkali metals. We notice that all have one electron in valence shell. And then if we haven't mentioned valence before, let's get into that right now. So valence, this is the largest orbital of an atom. The valence shell is where all the chemistry begins and ends. No chemistry happens in anything except for the valence shell. So where chemistry happens. That's super important. So the valence shell is really key to the behavior of an atom. Okay, the second group, the one that has magnesium in it and beryllium, these are the alkaline earth metals. And these alkaline earth metals, they all have 2 electrons. All have 2, and we can even call these valence electrons. The halogens is the second last group of the periodic table. This is this one, halogens. And the halogens are all missing 1 valence electron. Missing. So their valence shell is empty by 1. The noble gases all have a full shell. All have a full valence shell. What do you notice when you compare the first row, second row, and third row? So looking at the rows, we see that they are similar, but each row is 1 shell bigger. Oh, and look at that. There is 1 shell, 2 shells, 3 shells. So the number on the side, the row number, indicates how many shells the elements in that row have. Each element in the row has the number of orbital shells equal to the row number. Now, we don't need to know any more about the atom. That's enough for this unit, although there is some interesting things to happen because this model is from 1913, so there's lots of other stuff that's happened since then. For example, there are more than 3 orbitals. After the first 3, the number of electrons increases to 18, and then 18, 18, 32, 32, 1, 2, 3, 4, 5, 6, and 7. So that's 7 shells. but it does get a little bit strange. The way that electrons organize themselves is they don't always organize themselves nicely into those 7 shells. So we don't do anything past this one, past the 3rd shell, just because it's not very clear, or it's not easy to discuss the other shells. The atomic orbitals are not just spheres, they are actually better described in many different shapes, and these shapes have influence on how they do chemistry. The atom weights don't perfectly match up with the number of protons and neutrons, and if you figure that out, then you can actually develop the atomic bomb and nuclear power. It turns out that there's some energy that's lost and gained by reorganizing the nucleus and changing its atomic weight. That's the whole E equals mc squared. The m is the mass, E is the energy. So the reason the mass is not exactly this right is because there's some energy that is exchanged when we make new atoms. The electrons are also so small that we shouldn't really describe them as particles. This little circle with the dot on it is not really the best way. What we kind of want to think about is either thinking about them as being waves, and I can't draw a de Broglie pattern, but they could be kind of like a wave moving around the nucleus, or even better is to think about them as sort of a fog, where there's the electron is somewhere, probably right in the center point, but you can't know for certain where exactly the electron is. And so that's a model we'll talk about in a much later lesson in grade 12 chemistry. So that's something to look forward to, of course. Now, protons and neutrons are not the smallest particles. There are also things like the Large Hadron Collider that are doing experiments to find the other smaller particles like gluons and muons and others. And those help explain how a proton and neutron can actually become one or the other through something called beta decay or beta capture. But that's for the future. That's something you can talk about in your grade 12 physics class. Okay, so we are going to talk about the periodic table next. The periodic table was developed by Dmitri Mendeleev and Julius Meyer, and both developed tables for organizing the known elements. Mendeleev published his first, and that made him sort of the go-to name of the periodic table. He took the earlier classification of elements and he put them into a bigger idea called the periodic table. So he discovered that with few exceptions, that arranging elements in order of their increasing mass across rows and then organizing their properties in columns would cause them to obey something called the periodic law of repeating characteristics. He believed that missing elements had yet to be discovered, and so he left spots open, and those spots actually predicted a future element. This is the power of models. He took this model that he said, well, it appears that nature is repeating itself in a known pattern. So what if we apply this model of a pattern that So he's essentially saying that mass increases this way, increase, and then groups that are similar, and these would be similar properties. And in doing this, he ended up organizing his elements in appropriate ways and predicting where elements were missing. So things like silicon and germanium and a couple of other interesting gallium, indium maybe? Some of these other interesting elements, they were discovered much, much later, but they were predicted by Mendeleev's experiments. So the exceptions to increasing atomic mass rule were iodine and tellurium. Mendeleev handled that problem by placing the elements in the periodic table according to characteristics and ignoring their atomic mass. So if you look at iodine and tellurium, their masses are actually inverted, even though on the periodic table, we expect iodine by its mass to be smaller than tellurium, but in fact, by their behavior, iodine is placed to the right. Moseley solved Mendeleev's problems by arranging elements in order of increasing atomic number, and this solved all of the problems of atomic mass. So now, much, much later, we now have a periodic table that is very functional and very predictive and it allows us to do things like design experiments or design materials by simply looking at the periodic table and thinking, okay, if I want these properties, maybe I can move one to the left or one to the right and create a new chemical that has these properties simply by looking at the way the periodic table is arranged and designed. So periodic law is the properties of the chemical elements reoccur periodically when the elements are arranged from lowest to highest atomic number. So think about it like a ribbon, right? Think about you had a big giant ribbon where you've arranged all the elements, hydrogen, helium, lithium, beryllium, etc. And then you've sort of looped it around so that hydrogen and lithium, because they share properties, they're closer together. And then you loop around again so that you get sodium and sodium here, so that all of the ones that have similar chemistry, and then increasing atomic mass, or atomic number, not mass. That's what Mendeleev thought. So here's our periodic table, and we can see the atomic number is increasing from left to right, but the groupings, these organizations in the vertical, these are the families. And so we have things like the alkali metals. So the alkali metals is right here. We have the alkaline earth metals. We have chalcogens and halogens. We even have over here, we have the noble gases. Okay, so each of these groups has a certain behavior that we can depend on and trust and expect. So the periods are the rows of elements with increasing atomic number and mass, and 2 is the chemical families. These are the columns or groups, and they come in a bunch of varieties. I think we'll go through each of these families individually in our next video. I don't want to do too much today, and I would love it if you could go back and look at your Bohr model. Now, I want to make one more connection here. Looking back at our Bohr model, thinking forward, why do these similar, why did, when we look at the Bohr models now, we're looking at an organization of the elements by what Mendeleev discovered. So Mendeleev organized them by experiment. But if we had these Bohr models in 1867, we would probably organize them by this final shell, by the valence shell. So the valence shell is chemistry. All the chemistry comes from that valence shell. This outside shell is the chemistry. So that's the reason why these groups are grouped the way they are. We have all the alkali metals in a row because all of them share the same type of valence chemistry. All the alkaline earth elements share the same type of valence chemistry. They have the same elements, the same number of electrons in that valence shell that gives them the same combining power, the same chemical power. The noble gases, by having a completed outside shell, all share an identical behavior because their outside shells are the same. So valence is chemistry. Valence is chemistry. That's all I can say. Keep saying it to yourself until you get it. It's super important. All right. Looking forward to talking to you again in the next video, and have a great day.